Before we get started, what do you call a confused tree? Stumped. I know, you missed them over your spring break, didn't you? You don't have to tell me. I can see it in the joy of your eyes. Okay. We're going to, it's not advancing. Let's try this again. There we go. We're going to start here. So on your notes page, I have a copy of your notes page up here on the board. Should look like this. We call it Boyles Law after Robert Boyle. He did experiments with gases, and he found his experiments proved there is a connection between pressure and volume. So it's not just that he played around with gases, but he did very careful experiments that actually we could prove that this is something that works all the time. All right. What I want to do is I want to start off by showing you the graphical relationship of this. So move on over to that little graph that I put in the top right corner. Again, your name could be above the graph. I tried to leave that corner empty for your name. Need to let someone in here. Okay. There we go. We're going to start off by graphing, because when we graph and look for relationships from the graph, we can often tell some very important things. So we're going to graph together. You can see I have my pressure versus volume graph. So I'm going to put pressure on that axis, the y-axis, going to put some volume then on the x-axis. And I'm going to look at the pressure, and I need to start at 10 and end at 24. It goes by twos. That doesn't mean my graph's going to go by twos. But what if I did? Let's see how that would fit. If I called that 10, then 12, 14, 16, 18, 20, 22, 24. Yeah, that would fit well. So we're going to do that. I'm going to call this 10, call this 12, 14, 16, 18, 20, 22, 24, I could go 26, 28, so on. You get the idea. Our graph doesn't have to start at 0, 0, so there's really no reason to start at 0, 0. I hope you see I would be starting at 8, and that's okay. It's the way that would be. And this graph, it would end at 28. Don't necessarily need to label that because my data is not as far up as 28, but we could certainly extend our line. There they are. There you go. We just got started on the graph that's in the top right corner. Okay. Now on the bottom axis volume, this is going to be interesting. I have to go from 1 to 2.4. And it's got some not easy numbers in between, but that's okay. I don't label my graph that way. I'm in control of the graph. So let's see. If I called this 1 and I go by 0.2s, can I get to 2.4? Let's just count it out ahead of time before we do anything. So 1, 1.2, 1.4, 1.6, 1.8, 2, 2.2, 2.4, 2. Yes, that's going to work just fine. So that's what we're going to do. I'm going to call this 1 and 1.2, 1.4, 1.6. There's a point there. 1.8, 2.0, 2.2, 2.4, and I could keep it going if I wanted to, 2.6, so on. You get, and this, I could even label back here 0.8. So my graph does not start at 0, 0. It starts at 8 or 0.88, and that's okay. Graphs can do that. Point is, I counted it out ahead of time to make sure it fit before I did any of the labeling. By the way, pressure is, these are going to be in atmospheres, and volume, this is going to be liters. So I've got the labels for my axes, everything set up. We're just going to start labeling. My first data point is 10 and 2.4. So at 10, I go over to 2.4 and I'm going to put a nice big dot. I like big dots so I can see where my dots were even once I draw the line through it. That's a great way to do graphs in science, is to still know where your dots were. 12 and 2, so 12 and 2. 14 and 1.71. I don't have a line for 1.71. Am I going to guess it? Yeah, I'm going to guesstimate it. It's going to be like right there. We understand when you graph that there's guesstimation involved. It's totally okay. 16 and 1.5. Again, I don't have a 1.5, but I'm going to guesstimate it. It is clearly right in between 1.4 and 1.6. So I have a good guess as to where that's going to be right there. 18 and 1.33. This is going to be interesting because I want it a little bit closer to the 1.4 than the 1.2. Do I expect you to graph this by hand and get it dead on? No, no one does. We all understand when you're graphing by hand, you're going to estimate where to put those dots, and that's totally okay. Because we're going to fix it all up in a moment anyway. Okay, 20 and 1.2. Now this is going to be pretty easy. There's my 20, there's my 1.2. Going to put a big dot there. 22, 1.9. That's almost a 1.0. Nope, don't look at that. Sorry. That's going to be a little bit more like there. There we go. Something like that. And then 24 and 1. And then there we go finally. Okay. Do you have a very good idea of the way my line's going to look on this graph when I can draw it? Now, I want you to know we're not going to connect the dots. Okay, please hear me say this. We're not going to just connect the dots. We want one smooth line. Okay, so I'm going to smooth out the line. I'm concerned more with smoothness than connecting the dots because my line, when I take one smooth line, is an average. And having an average would be super helpful because I guesstimated to put those dots on. I'd much rather work with an average than with guesstimations. So I'm trying as best as I physically can with my pen here. I'm trying to make one smooth curve through it all. Oh, look, I didn't go through all the dots. Okay, that's okay. Again, a lot of those dots were guesstimations, and having an average makes it all better. So there we go. Now let's talk about this. This is down here at the bottom. Am I going too fast? Everyone got a line? Okay. Let's talk about this at the bottom. Help me out here. As the graph shows, as volume goes up, so as I go this direction on my graph from left to right, is the pressure going up or down? Yeah, it's going down. So that blank is down. As volume goes up, pressure's going down. As one goes one way, the other goes the other way. We have a fancy word for that. They are, and I don't know if you've ever heard this in math class, it is a math word. They are inversely related. It means if one goes up, the other goes down. If one goes down, the other goes up. So I just chose to look from left to right. I could have looked from bottom up. I could have looked from up down. I could, any way I go, I know the other's going to do the opposite. That's the key of knowing they are inversely related. Everyone good there? Got that written down? Okay. Let me know if I go too fast. Now, I want to have some fun and do some examples with you. And this could be interesting, trying to make it something that the online students can see just as well as you in the classroom. So we're going to kind of figure out what happens and go with it here. Okay, I need to see if this is visible. No, it's not quite visible. Okay, online students, I'm gonna stop sharing in a minute so you can get a better view. Let me show you what I've got going on, and here's what you want to write down. Okay, I'm going to be in the left boxes. Where's my pen? Oh, good, there it is. I'm going to do use a vacuum pump. I think I totally misspelled vacuum. That's 1C, 2U's, 2C's, 1U. I don't remember. I know, whatever, write vacuum, however you're supposed to. I've got a vacuum pump going on. And what we care about is what's in the bell jar. So there's the base, here's the big jar. And right now I have 2 balloons just shoved randomly. Those are supposed to be balloons. Man, good thing it's not art class either. Can't even draw circles. There's my 2 balloons. Now, right now, pressure is, we're just going to say normal. Okay. So right now I have the bell jar, 2 balloons blown up big enough to be shoved inside, but I can lift it up off the pump and it's just normal atmosphere pressure going on here. Now, what do we know about the volume? What would you call the volume of these balloons? Like big, medium, small? Give me what you think. Small, okay. In the classroom, we're all agreeing they're small, so we're gonna call them small. That's all we're gonna do right now. That's good enough for this one. Okay, now we're gonna come back to the after. This is a before and after. We'll come back a minute to the after, but I'm gonna stop sharing so I can get the online to see, hopefully in a much bigger view, what's going on. Get my camera pointed at it. All right, there we go. Okay. Classroom students, if you want to like physically move closer to watch it, I'm totally good with that. Camera's pointing this away, so if you're on that side, no one's gonna see you. It'll be a little noisy, just be aware. Can't even find my on switch. Where's my on switch? There it is. Okay, we ready? It's supposed to be on. I had it working before spring break. I know, I'm like, oh, there we go. It'll take it a minute for you to notice. Okay. So what has the vacuum pump done? The vacuum pump has done what it sounds like. It has vacuumed out the air. What has happened to the size of the balloons? They've increased. Now, balloons are special. Balloons are these magical things that increase or decrease in size so that the pressure inside is always equal to the pressure outside. So if I see my balloons got bigger, that tells me they had to get bigger so that the pressure inside is now equal to the pressure outside. So that's what we got going on. Let's draw our little after. I'm going to share again. Okay, what is it like after? Now, what would a vacuum pump do to the pressure? Yeah, it lowers it. This kind of vacuum pump could not get it to no pressure at all. That'd be impossible for this kind of vacuum pump. But where's my pen? Oh, way over there. That's why. But it definitely is going to make the pressure lower than before. What did you see happen to the volume, the size of the balloons? They got bigger, right? Yeah, so let's go, I don't know, let's just say big. If I can find my little cursor, there we go, big. And let's draw a little picture. So here's my base, here's my bell jar, trying to draw it the same size as before. I don't think and now my balloons were like whoosh and whoosh, something like that. So the balloons were filled with the gas. As the pressure decreased around the balloons, the volume increased in the balloons in order to equalize the pressures. What would happen to you if you went to outer space without a spacesuit? You'd be like the balloon. There's gases in your body, not just in your lungs, like all through your blood vessels and everywhere. Lots of gases in your body, and the no pressure in outer space around you would make you end up like the balloons. So you definitely need a spacesuit in outer space, unlike the Marvel movies want to show you. Now, this is not on your paper, but I like to have some devilish fun. I'm going to stop sharing again, get a bigger view for the online students. One of the nice things about doing gas laws at this time of the year is these magical little creatures come out. I really don't like Peeps at all. I'd rather just eat a bag of marshmallows. But yes, we're gonna put Peeps in. Okay, but I have a blue Peep and a pink Peep, so we get to take bets on which one dies. Oh, well, oh, come on. There we go. I almost killed it, almost decapitated it trying to get it out. Okay, so I have a blue Peep and a pink Peep, and I've stuck them on a toothpick to try to sort of get them to stay together. It is. We will find out who survives. 2 will enter, 1 will leave. Maybe. Ah, they don't even want to stand up. Yeah, we're just going to do that. Okay. Need to get the balloons out of here. Don't float away, please. Thank you. Okay. And I want to move over here so that the online students can they get a good view? Okay. I don't know if I can set this here and have it work. Yeah. It'd be helpful if I could see what the camera is showing. Yeah. Nope, it's just showing empty space. Okay. I guess I'm just going to have to hold it here. Does that work? Yes. Okay. Students in the room, if you want to get closer to also see what happens to them, this is just for fun. Okay, we're going to take bets. Which one dies first, pink or blue? Pink? Everyone's saying pink. Okay, here we go. Let's see what happens. Yeah, you can see the little sprinkle shell. Well, yeah. Now, I don't know if my pump can get us to that point. I'm hoping it can. I'm wondering if there's like a leak of air somewhere. Okay, so actually, I don't know if you can tell, but the pink one has started deflating, meaning it is done. Whatever air in it has popped out. So I guess blue's the winner this time. That's a little unfortunate. I've had some much better battles. Okay, of course, by pulling all that air out of the peeps. Okay, so there's what it looks like, all without the gas inside the marshmallow, all shriveled up. Would you like to? Okay. Yeah, it's still squishy because it's marshmallow, but it's not light and fluffy anymore. We've pulled all the air out of it. Okay. So there we go. That's peep fun. Now, other things we have to discuss. I've got more that we actually are going to put down on the paper, but always fun to kill some peeps. Yes, it does. There's been some years where I named them after students before putting them in. So I was like, is Johnny or Freddie going to die? Let's find out. So, yeah, exactly. Name them after my least favorite students, which is why I did not say any of your names. So there you go. Okay. Next up, I do have another demonstration for you. I wanted to do one in the reverse of what we did. Now notice we made the pressure go down and the volume went up in the bell jar. I'm going to do the opposite here. I need to reshare my screen though. Oh, before I do that, I have another fun one. Sorry. I know I'm kind of all over the place today. It's happening. Oh well. So similar to the vacuum pump, I have a 2-liter bottle filled with marshmallows. Any of you know one of these things? They're called fizz keepers. They're a little pump that you're supposed to be able to put onto the top of your bottle, and you can pump air into the bottle to keep it fizzy longer. Spoiler alert, it doesn't work, but it really does pump air into the bottle. So I have a bunch of marshmallows in here, and I've already been pumping it. So this is high pressure, and now I'm going to release it and let the pressure go down. So if pressure goes down, what should happen to the volume? Should go up. So let's see how the marshmallows fare. Yeah, well, they can't pump that much, unfortunately. If I got it too high pressure, I'd be afraid of exploding the bottle. Don't want to do that. Let's not do that. Thank you. Okay. Now the next one for our notes. I mean, I guess if you guys, when we're all done and you've done your like 8 practice problems, if you want to try repressurizing it and seeing how great a difference you can make, I have no problem with that. But next one I have a 2-liter bottle with a balloon stuck in it. It is literally stuck in the middle. Trying to find my pen here. So this is my balloon in a bottle. Where's my pen? Okay. Balloon in a bottle. And so here's my here's my 2-liter bottle. I'm going to have a pump on the top. And right now my balloon is stuck in the middle. It does look more like a jalapeno than a 2-liter. It's so true. Obviously, there's a reason I don't teach art class. Right now, the pressure is, I just only put the balloon in, blew it up, and put the pump on. So the pressure is normal. And the balloon right now, let's just say is, well, let's just say the balloon's stuck. Let's call it that. Okay, because that's what I want you to see. So I'm going to now unshare this balloon in the bottle. This does take a while. But already you can see my balloon is getting to the point where it's not stuck anymore. So my balloon is able to move freely. What's that mean has happened to the size of the balloon if I can have it move freely in the bottle? Yep, it's gotten smaller. There you go. You got it. I increased pressure, exactly. And by increasing pressure, so let's just say from normal, it's gone to high. Is that okay? High pressure. Which pocket did I put my pen in? I can't find the pocket I put my pen in. That's kind of sad. Oh, I didn't put in a pocket. It slid under the phone. Okay, so here's my bottle again. But now my balloon is small enough it's able to move around. Got my little pump thing going on there. Pressure is high. That's supposed to say high. There we go. And what do you know about the size of the balloon right now? It's not stuck, so it must have gotten smaller. Now to reset this for the next time I use this, I'm going to put the balloon right about here in the middle again, and I'm going to let go. What should happen to the size of the balloon as I release the pressure? Okay, so I am letting the pressure now go down, and the volume of the balloon should go up. And there it is. It's now again stuck inside my bottle, unable to move. Okay. Okay. You're so close. Great analysis, because that's exactly the thing we're talking about today. The question was to make the cups of ramen noodles. They start with the liquid and the flavoring in the cup, and then they get rid of it. They remove the pressure in a very big container like my bill jar. That causes the water to turn into a gas. So it's literally evaporating the water, but it's not heating it up. So that's what we call freeze dried. It is drying it out. It's getting the water to come out, but it is not heating it up. That's the freeze part of it. So then in theory, your food is ready for you to add the water back in, and it's back to normal. Now, honestly, does anything really taste back to normal after you add the water in after freeze drying? No, but yeah, I mean, if you use hot water and it's got lots of flavor, especially salt, they use tons of salt in it, it tastes pretty good still, right? So there you go. So that's exactly the same kind of thing we're looking at today. By decreasing the pressure, they're able to literally get the water to evaporate out without boiling it and get it to freeze dry our stuff. Okay, so that's the examples I wanted to do with you. Next up, I have, there we go. Here's our formula. This is the formula we're going to be using to do calculations. Now, you already have the knowledge that if one goes up, the other goes down. We're going to do some calculations, use some numbers, and our numbers should prove the same thing. As one goes up, the other goes down. Okay. Yeah, so if you haven't grabbed a calculator, feel free to grab one real fast. We're going to do some examples. Okay. I want to point out the ones is the volumes before we do a change, and the twos is the pressure and volume after the change. And before we do the examples, please hear me well. This is of great help for figuring out, is this a pressure or is this a volume? Look at the difference in the way they'd be labeled in the question. The labels in the question for pressure are usually things like atmospheres, millimeters of mercury, or torr. The labels for volume are going to be milliliters or liters. Do you see the drastic difference? So if I tell you 300, you don't know, is that a pressure or is that a volume? If I tell you 300 torr, you should be able to come to the front of the sheet, find torr, and be like, oh, that's a pressure. Or if I tell you 300 milliliters, you should be able to come to the front of the sheet, see, oh, milliliters, that's a volume. So it will help you quickly figure out what number means what by the label. So let's do 4 examples, and then we'll hop into Canvas for 8 practice problems in class. So you can get help with them and knock them out without having homework. I don't want you to have homework. And as I read this, one of the things I do, which I would suggest you do, is I like to circle the numbers as I read, but I make sure I circle the labels along with them, because I just pointed out how the labels are super helpful. So on the back of your worksheet, this is problem number 1 in the top left corner. A 4.200 liter, okay, so I'm going to circle all that, 4.200 liter weather balloon is filled on the ground where the pressure is 750.0 torr, so I'm going to circle that. If it's released and grows to 12.80 liters, going to circle that. In volume, what's the pressure around the balloon? All right. Now, I know my equation has P1s, V1s, P2s, V2s. Let's make a quick little chart here and list what we know. What would I call the first pressure? Yeah, use the labels to help you. Pressure would be measured in liters or torr. Well, not liters, so let's go with torrs. P1, 750 torr. What would be volume 1 then? There you go, 4.200 liters. What about pressure 2? This is kind of a trick question. I got you. Yeah, exactly. We don't know that. That's our X. That's what we're looking for. Okay, and then volume 2 was 12.80 liters. There we go. Okay, so here's our formula. P1V1 equals P2V2. Let's plug in everything. 750.0 torr times 4.200 liters equals X times 12.80 liters. What am I going to do to find my X? Exactly. Let's divide everything by 12.800. I've lost my pen. Where'd my pen go? Oh, it's way up there. That's why. So 12.80 liters. Cancels out on that side. And also notice this, liters cancels liters. So do me a favor, take 750 times 4.2, divide it by 12.8, and what do we get? And I know I went quite fast, so I'm trying to wait here for you to catch up on what I've written. And then put in your calculator. 750 times 4.2 divided by 12.8. What do we get? Try again. Yeah, divide by 12.8. Okay, don't forget to divide by 12.8. Oh, great question. Where should we put the decimal? How many numbers in 750.0? How many in total there do you see? 4. And how many over here? 4. And how many over here? 4. So let's go to 4. Let's just match, just like we've been doing. Okay, so 200, I don't know why I'm writing a 1. 200 what? 0.1? Okay, we'll go 0.1. And what's the label? Look what hasn't canceled towards my label. There we go. So that's all there is to these kind of calculations, but I do want to point out what happened to the volume. It went from 4.2 to 12.8, so it went up. If volume goes up, what should have happened to the pressure? Should go down. It went from 750 to like 250. Yeah, it went down. So the math and what we've been seeing matches up. One goes up, the other goes down. Any questions about this first example? Okay, we're going to go through the next two examples, and we're still going to have like 45, 50 minutes to do the practice, which should be plenty of time because there's only 8 problems in Canvas. And I'm here to help you through them if you need them. While packing for a trip, an almost empty shampoo bottle has 500 milliliters of air in it, and it has a pressure of 770 millimeters of mercury. While on the plane during the flight, the pressure in the cabin becomes 550 millimeters of mercury. Don't know if you knew, but the pressure even inside the airplane decreases as we go up. It is more pressurized inside the plane than outside the plane, but they can't prevent it from going down a little. Any of you ever traveled and have your shampoo bottle explode on you? Like on an airplane? Okay, hand sanitizer, not shampoo, but yeah, I mean, okay, so yeah, okay, so now we're like, oh, this is why. So when I went to Europe during college, one of the advices that I was given was if your bottle is not completely full of your sanitizer or liquid, squeeze out as much of the air as possible before you go. And I was grateful I got that advice because it worked well. Let's make a little list. P1, V1, P2, V2. I know some of you are just ready to go. I don't blame you. I get it. What would 500 milliliters, what would that measure? Volume, 500 milliliters. And then I have 770 millimeters of mercury. So that would be pressure. And I have a 550 millimeters of mercury. So that's also a pressure. And you got it. And I see 4 digits, 4 digits, 4 digits. We'll round to 4 digits in the end. That's exactly what we will do. So I got P1 V1 equals P2 V2. Let's substitute in our numbers. And I keep the labels there so I can keep track of what cancels out and what doesn't. It's a great way to know what your label's going to be. Now, by now, I hope you're noticing it's going to be very similar to what we did last time. I need to divide everything by 550 milliliters. Wow, no, millimeters of mercury. What am I saying? Sorry for saying that wrong. Let's get that right. 550 millimeters of mercury. Okay, so do me a favor. I need 770 times 500 divided by 550. I'm expecting a number maybe around 700 or even 600 something. 700 what? Even, okay, 700. How do we get 700 to have 4 numbers? We had a decimal and a 0. And the label that hasn't canceled, check this out, is milliliters. So that's what I know would be on my answer. There we go, 700 milliliters. Now, I know I went fast through that, but a lot of you were like racing ahead of me, which is totally awesome. Any questions about this one? Okay. Let's go to example 3. So bottom left corner. An average human can hold 6 liters of air in their lungs, so I'm going to circle that, at normal pressure on the shore. The record for free diving, that's diving in water without any equipment, is to go past 700 atmospheres of pressure, where the volume in the lungs is only 0.86 liters. Yeah. So under the amount of water that's the record for free diving, there's enough water pressure on you. It's like having 7 atmospheres pushing on your body. Notice what it does to the size of the lungs. It literally would squish them from 6 liters to 0.86. That's a huge, I mean, I can't imagine that you could live through that, but clearly you can because people have done it. Yeah, you do massive training for stuff like that. Like don't sign me up for that. I'm not into that. I'll go play in the ocean, okay, but I'm not going to do that. Thank you. What am I going to call 600 liters? Or sorry, 6 liters. Liters. Would that be a pressure or a volume? Volume. So that's my V1. And what would I call 7 atmospheres? Pressure, but notice, this is my second pressure. And my second volume is 0.86 liters because I'm looking now for P1. So just be very careful. So it's X times 6 liters. We're going to do very similar to what we've been doing. The equation is quite boring. To get my X by itself, I'm still going to divide by 6 liters. And I can see liters label cancels liters label, so atmospheres is left. So I'm going to have 7 times 0.86. I'm going to divide it by 6. Someone do that for me. I'm expecting this to be a pretty small number compared to 7. 1.0? Okay. How many digits did my 6, 7, and 0.86 have? 2. So let's go to 2 numbers. 1.0. Label that didn't cancels atmospheres. Boom, there's my answer. At the shore, before this diver got started, it was 1 atmosphere pressure around the diver, which is what we consider normal. Normal atmospheric pressure is 1 atm, 1 atmosphere. Okay, say that again. I'm not. Okay. Yeah, why did I put the 7 atmospheres for pressure 2 and not for pressure 1? Okay, so there was a break in the situation here between these 2 sentences. That kind of told me these 2 went together. And then the other big clue I had was it asked for the pressure on the shore, and that's where my guy was originally standing. So reading the question well is going to be helpful, and I tried in our practice to make sure that it's a lot clearer than the ones I'm giving you here. I wanted to give kind of more of a story with these. But good question. Be sure you're thoroughly reading to know what you are given and what it counts for. And that's why we're going to do the practice in class, so I can even help you with that and check over it with you on that. All right. One last one, and then we're going to get to the practice in Canvas, and I'll be here to help you out. The barometric pressure during a tornado is 11.9 psi's. Oh, I did not give you psi's earlier, but you know what? That's okay. Anyone know what psi stand for? You're so close. Not pressure per square inch, but pounds per square inch. So very close. Pounds per square inch. Not a scientific way of measuring pressure, but definitely an American way of measuring pressure. So during the tornado, 11.9 psi's. After the tornado, I have, oh, I need to click back over here. Well, I did not mean to do that. There we go. After the tornado, I'm back to 14.5 psi's. And the volume in the air after the tornado is 3.85 liters. That is a great question. So we have two pressures. Which one's pressure 1? Which one's pressure 2? The true answer is it doesn't matter. However, since I'm starting about talking about the tornado, let's call the tornado information pressure 1. So pressure 1, let's call that the 11.9 psi's. So what's my 14.5 going to be then? Pressure 2. And what was the volume at that after tornado pressure? 3.85 liters. Now, like I just said, if you accidentally mistakenly call pressure 1 pressure 2, it would not matter as long as you have the right volume to go with it. You would mathematically get the same answer, whether you call it 1 or 2. What's that mean for my volume 1? That's what I'm looking for. That's my X. So pressure 1, volume 1 equals pressure 2, volume 2. I'm going to take 11.9 psi's times X to get 14.5 psi's times 3.85 liters. Let's divide by that 11.9 psi's. And how many digits do you see in everything? 3, so let's keep 3. So what do we get for the volume of my bike tire during that tornado? 4.69. And let's see, PSIs have canceled, so liters. Now let's double check that. During the tornado, it was high pressure. After the tornado, it got to be low pressure. So the pressure went down afterwards. What should happen to the volume then afterwards? Should go up. My volume started at 4.69 and ended up at 3.85. So that does not seem to match. I think I said this wrong. It is not the numbers, it's me. I'm sorry. Let me try this again. From during the tornado to after the pressure went up, that sounds better. There we go. I was thinking that was 19 for some reason. Darn you, dyslexia. Pressure went up, so the volume should have gone down, and the volume went from 4.69 to 3.85. So yes, it did go down. It does match what we got. All right, so there's an example of one of each type of solving for whether it's P1, V1, P2, V2. Use the labels well to tell you if it's a pressure or a volume. Practice will help you figure out if it's a P1 or V1, P2, V2. I did try with the Canvas pages to make them a lot more obvious. We decidedly have time here in class to work on this, so I could help you with every single one if you want. There's only 8. I try to keep it short and to the point so you could take care of it. So I want everyone getting into Canvas and taking care of the practice that you see there. And of course, online students stay online. So if you have any questions, you can ask. Classroom students, get into Canvas. I'll get out some Chromebooks if you would like. And again, you're going to